Hello, today we are going to discuss Lagrange's equation of motion from D Albert's principle. So we can derive Lagrangian equation from two ways. One is D Albert's principle, another one is principle of least action. Okay, first we are going to derive Lagrangian equation of motion from D Albert's principle. So we know D Albert's principle F minus P dot into delta r equal to 0, the Albert's principle. From that information, we are going to derive Lagrangian equation of motion. So consider n particles. N particle. Okay. The transformation equation for the position vectors of the particles are, if you consider Ri, so here the I indicate number of particles equal to 1, 2, 3, and so on up to n particles. Okay, Ri, these are the generalized coordinates q1, q2, up to qn. Okay, qk also there, q here, and time t also. This is equation number 1, where t is the time and this qk generalized coordinate, where this k represented number of 1, 2, 3, and so on in particle system. Suppose if you differentiate with respect to t, equation number 1, you will get this one. Okay, d ri divided by dt equal to partial derivative of r, partial derivative of q1 d q1 divided by dt plus d ri divided by partial derivative of q2 dq2 divided by dt plus and so on plus qk also there, partial derivative of ri divided by partial derivative of qk dqk divided by dt plus and so on plus dou ri divided by dou qn dqn divided by dt plus time also. Okay, dou ri divided by dou. So rate of change of momentum is nothing but velocity, that we are going to represent it like this in classical mechanics, like a dot product r dot, okay, which means velocity here, equal to this. I'm going to write like this: summation k equal to 1 to small n dou ri divided by dou qk. This one is the qk dot, okay, plus dou ri divided by dou. So if you look at the generalized coordinate, it is a very important concept. Uh, this by using this generalized coordinates, so equation in terms of generalized coordinates is there, which will give you only the static information, right? So we need to find the what happened in the system at that time. So we need to derive with respect to t also. Those coordinates we can consider here the generalized velocities, generalized velocities of the system. So here this q dot represented is q k dot represents the generalized velocity. So generalized coordinates, so generalized velocities and this generalized momentum. So these are all the important factors. So by using these relations, we are going to derive Lagrange and Hamiltonian equation and what are the relationship between the q and q dot like this. Okay. So first we are going to derive the virtual displacement of the given system. We already know what the virtual displacement formula. So here I'm going to write the virtual displacement of a given system. Um, the virtual displacement is given by this equation. Delta Ri equal to just I'm going to derive directly. Okay, so if you want to write, you can write like this. This is virtual displacement of the system actually, q1 and q2. Okay, and so on qk and so on qn. So this is the virtual displacement of the system. Just go for this one. You can write partial derivative forms. Partial derivative of ri divided by dou q1 delta q1 plus partial derivative of I divided by dou q2 delta q2 plus and so on plus delta ri divided by partial derivative of qk. This one is delta plus and so on plus final term partial derivative of ri divided by partial derivative of qn small n delta qn. So therefore, we can write the virtual displacement of our system summation k equal to 1 to small n partial derivative of ri divided by partial derivative of qk delta qk. So it's better to give the equation numbers here. This is our equation number 2. So this is our equation number 3. Equation number 3 is very, very important. Okay. This is our equation number 3. Okay. Let's go for first step. These are the basic information of Lagrangian um, equation of motion we can derive the using these basic steps. So since by the definition of virtual displacement do not depends on time, according to the D Alembert principle, this is our D Alembert principle, right? Summation I equal to 1 to n capital N f I p dot I. Here the I represented the number of particles in system, ith particle in the system, into delta Ri, virtual displacement. So this is our equation number 4, and this is also the D Albert's principle. So please go through these steps, then you will get easily derivation of this information. We know force can be expressed in terms of two terms, right? Just remember these two terms, Fia plus the side way. This is the constraint force, just remember. And I'm going to use this virtual displacement here. Just extend this equation. One more equation, this summation I equal to 1 to n fi dot delta Ri minus summation I equal to 1 to n p dot I delta Ri equal to 0. This is equation number 5. So first I'm going to solve this portion. This is part 1. This is part 2. So then I'm going to combine these two equations for simplification. That is the easiest steps. Okay. So I'm going to use dr information here. We know that virtual displacement of the system. So this is equation number 5. So part 1 I'm going to solve. Part 1. This is part 1. And just I'm going to step by step solution. Okay. This is part 2 I'm considering. This is part. Please focus first part 1. Part 1. And here a delta Ri is there. I'm going to use equation number 3 here. Okay. Both parts. First part is, this is the first part. Summation I equal to 1 to n fi dot delta R, that equal to summation I equal to 1 to n fi dot, this is virtual displacement, this is summation k equal to 1 to small n, partial derivative of Ri divided by partial derivative of qk. In the q generalized coordinates, right? Delta q k. Then we can simplify this equation. Summation k equal to 1 to n summation I equal to 1 to capital N fi dou Ri divided by dou qk into delta qk. This is our equation number 6. So here this bracket information, here summation I equal to 1 to n fi dot partial derivative of ri divided by dou qk. I'm going to write like this. This is force. Okay. Here I'm going to write this force in terms of x, y, z directions. So f xi dou xi divided by dou qk plus f yi dou yi divided by dou qk plus f zi dou zi divided by partial derivative of qk. But for conservative system, the force is derivative from a scalar potential v, right? So it's better to write this. But for conservative systems, the force is derived from vector potential. Sorry, scalar potential. We write force can express in terms of F equal to minus del V, right? This scalar potential. Scalar potential V. So then we can write force in terms of potential energy minus del V. This is I. So if you want more clear this one in terms of vectors form, dou V divided by dou xi plus j dou V divided by dou yi plus k dou V divided by dou zi. So first part, summation I equal to 1 to n fi dot dou ri divided by partial derivative of qk equal to minus summation I equal to 1 to n. So here f is there, right? In our equation, f we can write dou v divided by dou x. Just replace fundamental equation. This is the fundamental equation. Just replace that. Dou v divided by dou xi. So we already have this one. See what we have here. Dou xi divided by dou. Okay. Dou xi divided by dou qk plus dou v divided by dou yi dou yi divided by dou qk plus dou v divided by dou zi dou zi divided by partial derivative of qk. So this is v, right? This is v. So we can express this one minus dou v divided by dou qk I'm going to give this one equation number 7. So if you look at carefully here, this portion I solved. Equation number 6 is there, bracket from square bracket. So this portion I took. So I got information this one minus dou v divided by dou q. Okay, just use that information here. This is all simplification. These 4 steps are simplification of this square bracket. Okay, please go through these steps. Okay, then you will get the answer here. Then I'm going to rearrange the equation number 6 like this. Just start substitute. Clearly, I'm giving equation number 1, 2, 3, and so on up to n equations. Substitute equation number 7 in equation number 6. Then we get this equation. First portion is complete. Okay, f I dot delta ri equal to summation k equal to 1 to small n minus dou v divided by dou qk into dou q. So this is our first part information. Okay, very important information this. Then I'm going to give this equation number 8, Borden equation. Second part also there here. So one portion is complete, this one part. Second part is there, minus also there. Then we need to focus only this term. And combine first part and second part, you will get the Lagrange equation of motion. Okay, easily. P dot delta R. I'm solving part 2. Okay, part 2. This is our part 2 term. Summation I equal to 1 to capital N, rate of change of moment P dot delta Ri. So use virtual displacement delta Ri value. Just wait. Just wait. Okay. Summation I equal to 1 to N. This is Newton's second law. Mi acceleration I'm going to write it like this, R double dot I. So virtual displacement summation k equal to 1 to small n. Okay, partial derivative of Ra divided by partial derivative of qk into delta qk. So for our simplification purpose, summation k equal to 1 to n, summation I equal to 1 to capital N m I r double dash I dou r I divided by dou qk. Going to put one bracket like this, like we derive part 1, delta q. So here this is our bracket term. Just simplify this equation, bracket term. Okay. Here summation I equal to 1 to capital N m I double derivative Ri dou Ri divided by dou qk equal to summation I equal to 1 to N. Okay. Here two derivative is there. I'm going to use one derivative here. We know d by dt of uv, derivative of u minus derivative of v, right? I mean u constant, v derivative minus v derivative, v constant. Okay. So you just follow that formula, d by dt of one derivative m I ri dot dou ri divided by dou t. Now this portion is constant. I'm going to derive to this one, minus m I r dot I is constant, d by dt of second term derivative dou ri divided by dou q k. I'm going to give this equation number 9, very important. So if you look at here, some derivation, important derivation, d by dt of, so this term dou ri divided by dou qk equal to, or else I'm going to write this one like this, d ri divided by dt, or rate of change of position is nothing but velocity, right? So this one dr divided by dt is velocity. Remaining term, this one is dou by dou qk is there here. So in place of dri divided by dt is nothing but velocity. Just put velocity term. So I got this one, d by dt dou ri divided by dou qk equal to dou vi divided by partial derivative of. So here I'm going to use, in place of this term, dou vi divided by dou qk. So here dou ri divided by dou t is there. So if you carefully look at this one here, dou ri divided by dou qk equal to dou vi divided by d by dt of dou qk, right? So I'm going to use dot product. This dot product represented d by dt. So this information I'm going to use here. Here dou ri divided by dou t. In place of dou r divided by dou t, I'm going to use dou vi divided by dou q dot velocity. Here dou v divided by dou q only. Generalized coordinate here. This is generalized velocity here. So please careful while solving this equation. So from equation number 9 itself, this is equation number 9. I'm going to rearrange the total equation. M I r double derivative I dou r I divided by dou qk equal to summation I equal to 1 to n uh, m I r dot I. Here I am going to write dou v divided by dou q dot d by dt m I r in v I am going to write here vi. So why here r dot I, right? So r dot is nothing but velocity. So just write r dot dou vi divided by dou q k dot, okay, minus m I r I dot dou v divided by dou q. So this is our equation, important. Uh, Here r dot place I am replacing velocity dou r I divided by dou t. I am going to use dou v divided by dou q dot k. In place of dou r divided by dou k, I am going to use only the velocity term, this term, dou v divided by dou k. So this is the simplification of our part 1, part 2. Then we'll get easy steps. Remaining we can understand easily. These are the basic fundamental steps to solve Lagrange equation from the D Alembert's principle. So lot of derivation is there. You look at both textbooks in JEST and Goldstein textbooks. Just I reduce this derivation step simply e by dt. This portion, I'm going to write this one like this: dou by dou qk dot into 1 divided by 2 m I vi square. So if you derive to this one, you will get this one definitely. M I vi. This is r dot. In place of r dot, I am using velocity. Dou v divided by dou q. The next final step, this one. Summation I equal to 1 to n d by dt dou by dou q k dot into 1 divided by 2 m I vi square. So here also we can write dou by dou q k into 1 divided by 2 m I vi square. So if you derive this term with respect to qk, you will get this one. If you derive with respect to dou by dou q velocity term, this equation 1 by 2 kinetic energy, then you will get this one. Okay. So this is the kinetic energy of ith particle, right? Kinetic energy we are going to denote in classical mechanics, graduate and postgraduate, T, not Ke, especially in Lagrangian forms. So therefore, we are going to write this equation like this. D by dt is already there. 1 divided by 2 mv square, I am going to use theta, partial derivative of t divided by dou q k dot minus this is also kinetic energy term T dou q k. Here dou q k. So this is our second part of simplification. So where T is the kinetic energy of the system of n particle up to n particle system kinetic energy 1 divided by 2 mi vi square. So therefore the second term, this is our second term of our equation after substituting. If you want to take D Albert's principle, this is our second term, D Albert's principle. So after solving this equation, I got this one. Okay, this information I got dou by dou T dou Q K dot minus dou T divided by dou Q K into delta Q K. So this is equation number 10. If you want this derivation notes, just please comment below. I'm going to send this in PT form or document form also. This is equation number 10. Now substitute equation number 8, 10, equation number 5. This is our equation, right? Part 1 and part 2. This is our equation actually. So we know this term value right now. We know this value also. Just substitute this information here. We will get easily Lagrangian equation of motion from D Albert's principle. Substitute equation number 8 and 10 in equation number 5. So finally we are going to conclude this one. N minus, this is the first term I got, minus dou V divided by dou QK delta QK minus summation K equal to 1 to small n d by dt dou T divided by dou QK dot into dou T divided by dou QK into delta Q K equal to 0. Then summation K equal to 1 to small n. Just rearrange this equation d by dt into dou T divided by dou QK dot minus dou T divided by dou Q plus dou V divided by dou QK into delta QK equal to 0. Okay. Then summation I equal to 1 to n d by dt dou T divided by dou QK dot minus just rearrange this equation dou Q T minus V I'm going to. So finally came into the ending state of equation. Here the coefficient of square bracket for each delta q must be 0. Okay, therefore our equation is d by dt into dou t divided by dou q k dot minus dou by dou q k t minus v equal to 0, where this v, I mean potential energy does not depends on q dot. Okay, here the v does not depend q dot k. So therefore d by dt partial derivative of t minus v, okay, divided by dou q k dot. We can write this one t minus v because v does not depends on q dot. Minus is already there. Dou by dou q k t minus v, okay, equal to 0. So let Lagrange to kinetic energy minus potential energy, its name Lagrange L, is called Lagrangian. Lagrangian of the system. This final equation d by dt dou L divided by dou q k dot minus dou L divided by dou q k equal to 0. So where k equals start k equal to 1 to up to n. This is our final equation, Lagrangian equation of motion of the system. This is Lagrangian. L equal to t minus v is Lagrangian. This is the Lagrangian equation for conservative system. Remember this one, this word. Lagrangian equation for conservative systems. So this is all about Lagrangian derivation. Next class we are going to discuss Lagrangian fundamentals.